this idea, Patrick, is that in the future we'll all have multiple instances of self, and that one way to get started with that is to have one or more cardboard cutouts of yourself. Yeah.
Well, Kim, I would like to say that I have multiple instances of myself right now.
You do. Yes, I'm seeing that. Excellent. Well done. Okay. Yeah, but only one of those instances is talking, which is good. Yeah. Yes.
Exactly that. Sort of.
Unmute that one. Okay. Ooh, nope. This is
no, that's what we don't want. Yeah. Yeah, one of the coolest things that has ever occurred in the course is when Patrick gave an entire teaching session sitting on the back of a very weak-looking plastic chair, balancing himself the entire 80-minute period. And it's something it's like, don't try this at home. I don't want any of you to get seriously injured by trying to recreate that, but it was totally cool. So he's sort of a high energy person, which is good, right? I mean, otherwise life would be very boring if there were no high energy people. So.
I think I've just proved, Kim, that we can only have one instance of ourselves. If we have multiple instances of ourselves, there's always some kind of cognitive resonance, and we get something like all of years of consciousness. Or for some reason, Zoom was preventing me from muting my iPad. So I apologize. You're all going to be tiny, and it means that the camera angle is probably bad for everyone on this side as well. And I don't get to see you on a very large monitor, but I'm still going to try it like this. Is that going to work for everyone? Can you hear me?
Yeah.
This is fine. Okay, cool. Sorry for that. I have this like nice wall-mounted monitor now that lets me see everyone in like big in size, but it does mean that it's a little challenging in terms of cameras. Although, give me a second. I'm sorry for the tech. I just want to make sure that I can actually see all of you because I don't want to do slides today. This is the thing I was going to pitch as well, is that in fact I'd like to have an interactive Q&A. Sure. And I thought that this might be, oh, hey, this works now. Okay, cool. So I can now see you on screen. You're just going to see me looking up like this, which I realize is not eye contact and it's not very digital friendly. But I think it's still going to get
simulated, pretend eye contact. Yeah. So they've had 3 lectures from Osmer. They are also required to know certain content from Rich Sutton, even though he's not teaching them directly. So they've already had a lot of AI teaching, and we talk about AI just about every teaching session. Yeah, so they should be, prepared for anything, you know?
Great, that's what I like to hear. And I was gonna ask you all, I usually do the usual thing where I ask everyone who they are and what programs they're in, and then a little bit about what you know about AI. And so I'm going to try to roll with that general plan. But the way I'd like to do it, so Kim, you could tell me if this is in line with what you're hoping as well. I like going sort of at the end of the AI series because it means that I have the opportunity to answer people's sort of broad perspective questions or things that have been sort of dwelling in their mind since the rest of the AI series for this particular lectures. So my plan is going to be to go roughly through the concepts in a lecture I've given before in this class on the fundamental elements of artificial intelligence and machine learning, sort of the what's, whys, and hows of learning machines, and structure today's session, at least, in terms of a Q&A with respect to each of those sections. And so I'm going to try and run it a little fluidly, make sure there's time for discussion. If we get off track, I'm actually really okay with that because this is more about you being able to ask questions, all of the rest of you asking questions and getting what I hope are satisfying answers to things that might have been nagging in your mind regarding machine intelligence and its impact on society, rather than me just speaking at you for, say, an hour and 20 minutes, which I think we all agree is probably not the best use of any of our times. So that's the plan. Kim, is that okay? Can I roll with that?
Yeah, totally. Yeah.
Awesome. So in that case, let's actually just go around the wonderful box world that we have here with all of your various faces and introduce yourselves and say maybe your program and a little bit about why you're interested in taking this course. That would be great. That'll just help me to make sure I gear this appropriately. Maybe I'll call names out. Does that
Yep.
make sense?
Yep. Yep.
I think there's only 9 of us on the call, correct? Okay, awesome. How about Nicole?
So I'm a computer science student. I'm just taking an after degree right now. My first degree is business. My background in machine learning, or like what I know about it, I've taken like a couple machine learning classes in the faculty of computer science, and right now I'm taking like a class called machine learning, but most of my background has been more on the like learning what it is versus the applications.
Okay, fantastic. Thank you. Let's drop down. I'm using my arrangement. Maybe it's not what you see, but let's go to Ashley.
Okay. I am a 4th year physiology student. And I guess with AI, we have a lot of neuro classes, and they at this point are like, we need to integrate and let them learn AI. I also have like a healthcare background, so I know mostly kind of that aspect of it, and I find it really interesting.
Very cool. Thank you. Let's drop down to Taryn, please.
Taryn.
All good. We can go over to Kadya, please.
Hey, I'm Khadija. My name is Khadija. So
Khadija,
yeah,
my apologies.
it's okay. So I am a 2nd year PhD student in the Department of Medicine, and my work is basically around the area of allergies and asthma. And this is actually my last course in the degree. So I decided to look at something different angle. This will help a lot with especially with medicine and the new ways we can generate more ideas.
Great. Thank you.
Thank you.
Moving over to Leanne.
I'm a 5th year business student, and in terms of AI, like we learn a lot about just random buzzwords within business about how it can be applied, and there's like a lot of different ways and things that you can do with it. But I think I'm just more interested in learning kind of the details of it and what that might look like in terms of the future of work, and how that can help everyone in general.
Very cool. All right, up to Eduardo.
Hello, I'm Eduardo. I am a PhD student in the Department of Medicine. I am sitting geographically very close to Hadija. We work in the same lab. And about artificial intelligence, I am very influenced by movies. So sometimes they are bad and they're trying to kill us, and sometimes they are very good and they can help humanity. And the course has been very interesting. For instance, Dr. Osmar Sayan talked about how in the past word processors at some point were considered extremely smart machines and kind of artificial intelligence. But nowadays it's like, oh, that's Word from Office. We don't give that much thought to it as an artificial intelligence. So maybe our future, descendants will think of what we believe is AI as something very like, oh no, that's just the program that is always there. So anyway, that's me.
Cool. Thank you. And Kaylin?
Yeah, hi, I'm Kaylin. I'm in my 3rd year of marketing, so I'm a marketing co-op student. And the reason that I'm interested in this course is because I like Leanne. They talk a lot in business about, AI, machine learning, and they talk a lot about it, but they don't go a lot in depth. And so I thought this would be a really good chance for me to learn about those new technologies, how it influences the workplace, and then also looking forward to the ethics behind all this new technology.
Fantastic. Okay, great, folks. I think that's everyone, unless Taryn wants to jump in. If not, that's okay too. All good. And I guess I should also say that I think this lecture today probably ends a contest of wits I've had with Dr. Salez for many, many years now, where I have repeatedly tried to avoid his videographers, move out of frame, get my lighting wrong, and generally avoid in every way possible being video recorded during lectures that I give in his class. And now the inevitability of our digital platform means that I can't avoid being video recorded. And in fact, video is the medium by which I deliver my interactions with you. So Kim, I will cede victory to you.
Yeah,
You have
yeah,
won, you knew the future.
I
and,
did.
And it
I won. Yeah, totally. Take no prisoners.
Yeah, exactly. So that is the end of that particular battle of wits. So let's start with the first topic of the day. In fact, I think I'd like just to start with intelligence. And this is something that probably you all have various opinions about. I'm sure you have different thoughts or perspectives on what it means to be intelligent. What are the hallmarks of intelligence? But I like to start here. This is, if we're going to talk about machine intelligence, machine learning, if we're going to ground all of the ideas, if we want to even talk about how machine intelligence is used in marketing to serve ads, doing A/B tests or statistical learning to say which ads are better for which viewers. Oh, hey, no worries, Taryn. That's all good. I will try to monitor the chat window and if someone, Kim, maybe if you can also monitor chat to see if there's a question or comment I missed, then we can make sure that everyone's getting to have a proper voice. Okay, cool. So the idea is that intelligence is a squishy thing to try and define, and we should talk about that before we talk about artificial intelligence, whatever that means. So I just was hoping to hear from all of you, or whoever's willing to sort of put forward an idea. What do you think intelligence is? What are the hallmarks? What are the things that signify intelligence? And maybe you've got some answers you pulled from Osmar and Rich, but maybe you have your own perspectives. I'd love to hear them right now. I think that'd be a great way to open up this discussion.
That's a hard question. I would like to maybe open also the floor. I don't think we understand intelligence very well. For instance, some of us have pets, and sometimes animals are thought of as non-intelligent beings. However, if you have a pet, you sometimes differ from that. They are intelligent in their own way. And because I don't understand the intelligence of my pet, maybe I really don't understand what intelligence is truly. So,
yeah. I would point out, Patrick, that Eduardo has a lovebird, and the lovebird's usually on his shoulder during the call. Maybe the lovebird is on holiday, but birds are particularly interesting because their brains are quite small, but they're capable of many of the same things that we are able to do with much larger brains. So answer there that birds have found. Yes.
Good. We have very inexpensive professor replacements. We're just going to recruit a couple of birds. This would be fantastic. Good for cost savings as we refactor the university. So Eduardo, I have a question back for you. You know what? let's try something here. There we go. We're switching gears. I'm going to go back. I'm going to go to standing mode here. If that's okay with you folks, because that way I think everything will be properly aligned in terms of. There we go. Okay. So I'm going to standing mode so I can see you all a little bit better. Cool. So Eduardo, flipping it back to you. I mean, do you feel that like intelligence? I agree with you. We really don't grok all of what we should for defining intelligence properly. Do you feel intelligence is something that is binary? Like, is it a yes/no kind of question? Like bird intelligent, fish not intelligent, slug probably not intelligent, bacteria not intelligent, human arguably intelligent, or is it a continuum? Is it a single line, like some kind of particular, like a knob that you turn from not intelligent to intelligent? How do you feel about the dimensionality of intelligence? Maybe that's the hard way to phrase the question.
I would think it's a continuum, and there is room for every being to travel through that continuum from, let's say, less intelligent towards more intelligent, but there needs to be some sort of training and maybe some sort of guidance, and maybe whoever is learning needs to see how things are organized, and then based on that organizational system, then they make their own algorithm to organize information or whatever their input is from the environment, and then how they interact with it. So yeah.
Cool, thanks. So now that's a great way to open this up to everyone else as well. So with respect to the dimensionality of intelligence, what are your thoughts when you look around at the other systems that are in the world around you, everything from thermostats to dogs to university instructors? Do you think of those as a yes/no kind of question? Do you think of them in terms of different axes? How do you think about intelligence and its dimensionality? Please.
I think intelligence is kind of like on a scale of, we think of it as a concept of, especially with like animals, how much can they understand us or follow our rules or be the most similar to us. So we kind of equate intelligence as humans are at the top, everyone else, if you're closer to us, you're more intelligent. And then we equate each other of, if you're average, you're okay. If you're smarter than the rest of the humans, you're more intelligent. So it's kind of like a rating scale against the average human.
Cool, and that's a neat way to think of it, because you're suggesting that in fact maybe that absolutes are not the right way to think about intelligence, and that there's a relativistic way, or maybe that one of the only grounded ways we can think about intelligent systems is with relation to other intelligent systems that we know. Does anyone else have feelings on this?
I feel like in terms of intelligence and the way that we measure intelligence is very interesting. Like for humans, we measure it along, IQ, but there's so many other different measures of intelligence, emotional intelligence, or even looking at the way that different animals adapt. Like we learn from ants, for example, who work in teams to move pieces of, wood for their home. And is that intelligence, or what is intelligence? It's a big question, honestly.
Cool, thank you. Thanks for sharing that. Any other reactions to this particular question of dimensionality? Try ask another thought-provoking question. Okay, I'll ask another question then. Is there, for those of you, who haven't joined?
I would just like to add something. Like, I feel like the way we think of intelligence is something that's behind our capability would be something intelligent to do. It's almost relative to what Ashley said. But for example, something maybe we don't have ability to, but it is actually also intelligent for even, for example, one cell being like bacteria and viruses that can do something that we cannot do. Like they can modify their DNAs, RNAs, their genome, something that we can't do. That's intelligent too, but I mean, it's just in a different angle.
Awesome. Okay, this is really good. So then for those who haven't spoken yet, perhaps, is there a point where you would say something isn't intelligent? So I mean, there's like, we can talk about levels of intelligence, or in the way that some system might progress along the different axes of different facets of what we consider to be intelligent behavior. Is there any way that you might use in your toolbox of thought artifacts to say something is not intelligent? Is there a way that you could ever do that? Is there a clear-cut sort of rule of thumb that you use personally? Anyway, that'd be great to hear if anyone has a thought on that particular question.
I would say it's like, even going back to what has already been said, it's just so hard because I think intelligence is on a scale, and whether it's you have like less intelligence compared to the, as Ashley was talking about, compared to the average human, it doesn't mean you're not intelligent at all. And then kind of thinking about what Kylan said earlier, things are different, things are intelligent in different ways. And I think when you want to look at animals, the way that they've adapted over the years, that could also be a sign of intelligence too. And I think it's just so hard to have like an actual benchmark to say something's not intelligent at all.
Yeah, and I saw Taryn chipping in with a comment about plants. I mean, the idea that, and this is plants, actually, I was going to bring up thermostats. So plants are another really good one, because you could ask the question, and I know I've seen this posed by Rich Sutton, for instance, is, well, like, what do we think about the intelligence of a thermostat? And a plant that moves its leaves to track the light over the course of a day, there's analogies, similarities and analogies in both of those, in that we could see that they're sort of state response reactions. The thermostat could be viewed as an intelligent system, or it could be viewed as a simple and relatively rudimentary machine. Just, you know, keeps going until it stops moving, and then the temperature is clearly at the right level. Or at least it was when I had thermostats. Maybe everyone's got machine learning thermostats now, and this is a silly example. But back in my day, there were like these coils of metal that heated up and cooled down, and there's mercury in this. Anyway, maybe no one has those anymore. Maybe I'm just really old. But this is something I brought that example up, and the plant's another good example, because I think taking a page from Rich's book again, the idea that we might both mystify and demystify a concept. Intelligence is one such concept, and maybe you've heard this said to you already, and so I'm just repeating something. I think it's worth saying again, is that you could imagine when you look at a phenomena, you could try to mystify it. You could say the thermostat is absolutely intelligent, and then by taking that viewpoint, you can observe facets or aspects of it that you wouldn't otherwise. And you could say it's a brute force machine, and you would observe different things about it. So those two views are in fact compatible. You could hold both in your mind's eye, and even though that they are very, very different, you could believe both at the same time, even though they are different. So that's mystifying and demystifying, and it's a very useful tool. So when we approach intelligence, and especially machine intelligence, it's very nice to take that. So maybe this is a sort of a takeaway from this first phase of the discussion, that if you're thinking about, say, a language model, a big neural network, let's say, that does cool dialogue or generates it, like the GPT-3 from OpenAI, you could view this as a very magical style of system, a system that is able to respond to text that you type with almost, in some cases, flawless, or at least very convincing human-like language, and answer very complicated questions. Heck, DM a Dungeons and Dragons campaign for you. Wow, that's really intelligent. And you can also say, this is a very large language model where there's a series of connections, and they're using weights, and there's numbers, and there's registers on a drive somewhere. Like, this is another way to view it. By viewing both those, the intelligence as embodied by a system like, say, GPT-3, from both those views, I think you can learn something quite profound. Okay, cool. So then, with all of this in mind, can anyone pitch a definition of intelligence?
Silence. Oh man. Crap. Oh, sorry. No. Well, it changes over time. I mean, it will change over our, even probably our social input will change our definition of intelligence. Like, oh, you voted for X, then you're not intelligent. You know, things like that. So I guess that we could say that it is a continuum, but I really like what Ashley and Hadija were saying, that it is relative, and in a way we try to normalize it with the human scale, and we say, okay, everything is going to be measured in comparison to the humans. Then the humans are the baseline, and then there will be some that are more brilliant and some beings that are less brilliant. But I guess that if another very brilliant kind of being came into play, then we would be lagging, right? And then we would need to change that baseline if we decided collectively. So yeah, that's close.
Anyone else want to hazard a definition? The nice thing is that we don't have a right answer, so no matter what you say, it's like, yeah, that's awesome, cool perspective. Ashley?
I can say that intelligence is whatever we decide in that place, in that period of time, that something can acquire knowledge.
Cool. Yeah, no, that is, and the acquisition of knowledge, and even what knowledge is, I mean, one of my graduate students, Alex Carney, has been teaching me many things about how people over the course of philosophy have defined knowledge and the acquisition or retention of such. And so based on the flexibility of the different definitions of knowledge, we can imagine that is a definition that subsumes a lot of what we mean by a thinking system. Anyone else? Maybe Nicole, do you have a thought on this? I don't know if we got to you on the last couple of rounds. So
Just like a really simple definition, maybe like based on some of the like ones where we were saying like thermostat and stuff. But based on those, I was kind of thinking like something that can take like stimulus from their environment and use that information to make decisions or like make some sort of outcome.
Cool. Cool. And so the decisions or achieving outcomes is actually a really interesting thing. And maybe I'll branch in then. If anyone else has thoughts, please by all means jump in a second. But I'll just use this as a chance to say that one of the definitions of intelligence that I've actually found quite compelling. I know my colleagues also find this definition quite compelling. And maybe you heard it, comes from McCarthy, which is really thinking about intelligence as the computational part of a system's ability to pursue and achieve goals. Now that's a paraphrase. The actual quote is more precise than what I just said, but really the gist of it is in fact that intelligence is the computational part of the pursuit of goals. So that's a really nice, like that is something that we might be able to then ground ourselves in. It is maybe in fact it doesn't have to worry about the absolutes or the relatives. It doesn't have to really say whether or not something is very or little intelligent. It says that, oh, well, intelligence itself, the phenomena of intelligence, which Kurzweil has said is the most powerful phenomena in the universe. And quite frankly, I believe that view. I believe that particular statement, in part because intelligence can also be viewed, and some argue, as the carving out of order out of chaos, the fight with entropy, the inevitable organization of the fundamental elements of the universe. That you could argue that those things are true. That's the job of intelligence, whether or not it wants to or not. That is what intelligence does. And so then the computational part of the ability to attain goals or pursue goals really says, yeah, that it's a structuring or an ordering of all of the chaos that swirls around a system in the pursuit of the goals of that system. So that's a really neat definition of intelligence, because it doesn't force us to make some of the hard choices I think that we might otherwise make, and that we've sort of talked about in the last little while. Does anyone else want to chip in for? I'm going to shift gears here, I think, just in the interest of time. Does anyone else have anything else they want to comment about the definitions of intelligence, or a definition they want to propose?
Does that definition imply intentionality though?
Intentions and goals. So that's a really, that depends on your view on goals and intentions. As a reinforcement learning person, I'm sure Osmar and Rich's material has well grounded you in what reinforcement learning is like. It's really the attainment of some sum total of reward into the future of a system. Often we do think about systems as having goals, and so an intention though might not actually be, like, intentions and goals might not in fact be aligned, depending on how you think about each of those concepts. So I could intend to be doing something, but my intentions might be disconnected perhaps from my long-term goals. And so the objective might be something like survival. The objective might be something like, maximize the amount of something I gain. But I think the generality of a goal-based formulation is very consistent with how we view things, at least in reinforcement learning, but it doesn't necessarily mean that the system has a set of what we might consider to be intentions that align with that goal or do not align with that goal. There might be, again, some kind of other definition of intention that makes that sort of that comparison challenging. But I think it again depends on what view you take on intentions and whether you view intentions as in fact synonymous with goals. Does that help? Is that good? Cool. Okay, awesome. Anyone else want to chip in before we shift gears to the next segment? No? Okay, good. The obligatory, I'm giving longer pauses just because I know it takes a while sometimes to figure out if you're like me, where your mute button is, or like poke the bits of your screen you need to make contact. So I'm going to give longer time. So the awkward silences will be me waiting for you to have the opportunity to press the right buttons. I always fail to press the right buttons. Cool. So, okay. So if we believe that there could be definitions of intelligence that we appeal to, and we believe that intelligence is a phenomena that we might imagine, that phenomena can come to roost in many different forms. It could come to roost in biological systems, in mechanical systems, electromechanical systems, purely informational systems. You can imagine many places where intelligence might manifest as a phenomena. And the one I think that we're probably here to discuss is intelligence manifesting in machines. Now, often people say this is the field of artificial intelligence. Maybe Kim has heard me say this many, many times, but I'm not particularly pleased with the artificial tagged on the front, because again, if we believe intelligence is a phenomena, then any of its manifestations should be in fact real and not artificial. But all that aside, let's maybe think about intelligence as manifesting in a machine. Many of you heard probably many different names for intelligence as it manifests in a machine. You've probably heard AI, the big hypey thing that is really trendy. Machine learning, which used to be really trendy and now is like maybe less trendy than AI, but it sort of jostles back and forth. And then data science, which arguably is also machine intelligence in a different form. Pattern recognition, all these different names. Maybe I'm assuming you've all bumped into one or more of these, even outside of this course, but maybe, is that true? Have you all bumped into various forms of like the phenomena intelligence coming to rest in a machine form? Cool. Okay, awesome. So with that in mind, I mean, I'm guessing probably you have, where's my phone? Let me find my phone here. Oh yeah, so like these things. I mean, these things have various forms of intelligence system technology sort of baked in under the hood. And so I'd imagine that you've engaged with different forms of machine intelligence in all of the different digital ways that you communicate, even the way we're communicating right now. So with that in mind, maybe the next question, this is my next sort of question or discussion topic that I was hoping to bring up, and the usual flow for how I unpack the fundamental principles of machine intelligence, is what might a machine learn? So let's even go away from full intelligence. Think about a machine as a learning machine, a machine that might begin to learn or adapt through its interactions with the world around it. If we assume that setting, that the machine is actually not just like some massive system that was deployed that knows all of the things it will ever know, but that it is a system that might actually have to learn or change or adapt in its world, something I think that we do as biological organisms. What are some of the things that a machine might learn?
Whatever we input into it. So
Sure.
It can be statistics about the number of people in a city, the climate in a particular geographical place. But right now we are, in a way, the masters, and we're giving the machines that information that they are getting. That's what I think.
Cool. Okay, so this is a one very important statement, is that there are facts or statistics or input signals that we might provide to a machine and expect that machine to either memorize them or to modify itself with respect to those signals. So I'm sort of zooming out a bit from the specifics to try to generalize a little. But let's bounce around a bit more just to make sure we're collecting a gigantic bag of ideas before we try to distill them down into their fundamental groupings. Anyone else? What else might we expect a machine to learn?
I think machines can have, based on the inputs we give, can make decisions. And those decisions are based on what are we actually looking for. So for example, let's say a doorbell, and that has a camera that can recognize people and then open the door or not open the door for those people. We have inputs in the machine. So this is something that machine can do, is to have decisions based on the input we did.
Fantastic. So this is a great, I like the counterpoint between those two examples, because this example that you just gave really centers on learning how to make decisions, learning ways that it might act in different situations based on different inputs. And in fact, learning perhaps even the nature of the goals of other systems that exist in the world with it. So that's really cool. Like the human goals, being able to express our goals to a machine is also something that machine, our valuations, our breakdown of how we structure the world and choose to make decisions based on that structure are things that a machine might learn. Cool. Let's have some more answers, please.
Maybe algorithms or decision trees, or if it's this, then yes or no. So we can also teach the machine how to organize their inputs, and that kind of algorithm can then help the machine evolve.
Yeah, I mean, zooming back to the work of folks like Douglas Engelbart from the 1960s, the idea that you might expect systems began to form process hierarchies or specific methods. I mean, an algorithmic approach, like learning an algorithm is learning a method, is learning a process, and that is in fact something that indeed a machine might want to learn. From the folks who haven't chatted yet, or who haven't chucked in an idea, please, do you have any other thoughts about what a machine might learn?
I was kind of quickly thinking maybe even just problem solving, and that might be really general, and it's kind of, it relates to making decisions as well. But what I'm thinking about is, like in previous classes, we've chatted about the idea that machines can one day become more intelligent than humans. And there are obviously a lot of problems in the world that we haven't solved. And would a machine one day be capable of learning how to solve these problems, or like what inputs would they take, and how would they go about solving them as well? So I think that might be one potential thing that they'd learn how to do in the future.
Neat. And what's also cool about that is, I mean, there's specific terminology that we use in various subfields of machine intelligence. In various subfields, we might use what you just said and call it something like planning or model construction. Like this is only a small aspect of what you just proposed, but one aspect that I can imagine is in fact the nature of planning. I mean, planning either as a way of sequentially structuring paths through the future, or planning as a way of learning from remembered or imagined experience, and also model construction, building up an understanding of the way that the world works, or the way that the world flows, so that you can act within that flow. Those are also things that, yeah, we might expect a machine to learn a model of the world, or to learn a way of planning with respect to its model of the world. That's a really cool idea. Any more thoughts?
I think it's something that people don't really think of as a machine doing, but learning like what art is, or how to make art, or like emotions, or all of those things that we don't associate with machines at all.
Yeah. Oh, now I just want to go on Twitter and show you some awesome, like, emergent deep net generative art done by Revit Andal. Like, there's some amazing things where it's like a deep neural network trained on all of the landscapes across the world, and you can watch it morph one landscape into another in an incredibly artistic way, and like mountains will sprout out of clouds, and it's put to music. Anyway, there's like some beautiful constructive art, which is like largely, I mean, yes, it's a facet of the things that were input into the system, but then there's also a process that the machine has generated, has learned, for synthesizing and in some ways transmogrifying the inputs it's had into something that is inherently, in my opinion, at least beautiful. Anyway, so there's a very, very cool researcher who does this at a grand scale, I would say, to the point that it goes into art installations, but there's many others around the world that are doing very cool things. So let me zoom out a bit on that one and say that not just I really like the way these generative nets make really cool art, but that in fact that there are creative processes that might be learned. And this is partly a comment about, like, we heard algorithms and processes, but it's also partly a methodology for exploration. And so those are things that you might expect a system to learn a process or method, or a set of biases that allow it to explore the world. So that's another thing that might in fact be learned by a machine. Maybe a couple more quick answers, and then we'll go into a sort of a Q&A on at least one breakdown of the sort of super classes of what machines might actually learn. Going once, going twice. I'll give Kim a chance to answer as well, since we've left him out of the discussion so far. He chooses no. All right. So in that respect, then I think we can maybe zoom out a little bit, and I think that the typical way that I usually break down what a machine might learn, or what it might strive to acquire from the world around it, would include representation, prediction, and control. And there's also all the sort of meta control aspects that you might expect, its own internal self-regulation. But in general terms, usually I like to think about what a machine might learn in terms of what it might hope to predict, what it might hope to represent, and what it might hope to control. And let me just pitch those three categories to you, and then we can go into sort of a Q&A on each of them. I'd like to usually start with representation because it is something that is very fundamental to every learning machine that we have. And so if you look at the sort of we were in one of my my collaborators, Rory Dawson and I were looking through this just yesterday as to like the definition of representation, field independent, just what you'd find in the dictionary is like to display or portray something as being in a certain way. And so like you can of course roll back into the annals of philosophy and find all the different definitions of representation. You can ask about neural representations in the human mind, whether or not there's a grandmother neuron or a tiger neuron. You can ask about what part of a neural network in a machine, for instance, would be the part that encapsulates the pattern that detects grumpy cat on the internet. You can ask all these things, but in a grander way and in a simpler way, perhaps, you can think of representation as the way that a learning system structures the information around it. And this could be as simple as just taking in whatever signals from the world it is able to acquire, but it might be something more subtle and more complex, like the way that it might structure its internal mechanisms such that it can capture different relationships between the signals it perceives in the world, to maybe be able to have internal activity that relates to, say, the presentation with the face of a grandmother or the face of a dog or a cat, or the lab in you actually in Kate's group, Senator Eduardo and where are you? Are you actually in medical science? I'm trying now. This is my like representational mechanism.
We are at
in
the
the HMRC.
Okay,
Yeah.
cool. Okay, that I was like, this is very close to where my office is, and I know. but part of that is because there's these patterns that you could argue that I have a representation of the various spaces on campus, and there's bits of me that lights up when I see things that are familiar. In this case, sort of the general neck of the woods where you are.
The boxes dangerously placed on top of the shelves?
That looks identical to my lab. So anyway, no, I think actually we removed the boxes, but and the blue windows. But either way, so this is representation, and I think this is a great place to start. And there's lots of things that you could imagine in terms of how we discuss or see representation. This could be everything from how we imagine parts of a machine lighting up in response to stimulus. It could be the way that your phone and your videos streams right now are compressing information. Compression is in fact, and compression learning is in fact a aspect of representation. How you might take like the image of all of you and then squish it down to a couple of bits and then stuff it through a wire and then it unpacks on the other end. Like this is a representational act, and it's an act that might be learned by a machine. So with that first one, let's just start with representation. Do you have any questions about representation? Do you have questions about what kinds of representation a machine might learn, or why it's important for a machine to engage in the learning of a representation? Why there's an entire conference called the International Conference on Representation or Learning Representations. ICLR. ICLR. Yeah, ICLR.
I have a question. Is it interchangeable with interpretation?
I like that question a lot. Because part of me thinks that the answer is like absolutely yes. I mean, imagine you're presented with a set of stimulus like the video feed from you in your lab, and then one must interpret that as a member of a particular class, or as a point somewhere in a line of locations or spatial arrangements. You could say, well, yeah, actually, it is maybe an active interpretation, in that it takes a large number of things, it synthesizes them to something that maybe accurately compresses or displays or portrays the suchness of that stimulus or input pattern, but it does so in a way that is maybe more compact or more generalizable. There's different ways you might, depending on how you define interpretation. I think you could argue that, yeah, actually that representation and interpretation could be akin to each other, and especially in goal-directed systems. Or like an image classifier. I'm sure that Osmar showed you examples of systems that took images and then told you what those images are. Either said like, it's like 80% blue, or this is a dog or a horse. Like I'm sure did everyone just nods or thumbs up or something? You went through image classification and things with the other lectures. Okay, awesome. So, I mean, you could argue, I think, that because that in essence is a goal-directed system. It is a system that is like, it has a loss. It's being trained to optimize itself, to take inputs and give a correct output. And that output is in fact a way of categorizing or in other words, casting meaning upon the patterns present in a wide range of stimuluses. I don't, like, Eduardo, do you feel does that interpretation according to what you mean by interpretation?
I think yes, but that is very personal. I use the word interpretation, and it has more meaning to me than representation. So, and I think it's also because of my mother tongue. The meaning of the word in my mother tongue is different. So that's why.
Cool. And the other interesting thing is like the way that we speak of representation interpretation. I mean, we could think of it as a doing thing. I will represent something. I will interpret something. This is the act of interpretation or the act of representation. I think a lot of times the word representation as well is used, at least in the machine learning community, as the final structure of a learning machine after training. In say the case of supervised learning, of learning through labeled examples, you might say that, oh, well, I have this big fancy deep net and it's got all these like building blocks. For those who know deep nets, you might like, I don't know, the conv net's connected to the conv net, the other conv net's connected to the LSTM, and then like, you know, all those other things that happen. And there's like gradient stops. And anyway, but that like arguably, once that structure, the knees and bones of a neural network, the head and torso and the feet have all been populated with the weights that are learned through the input of data, a lot of folks would say that that is the representation. It's a thing, it's an artifact, it's an object you can hold in space and stare at. And that is in fact the representation. And this is not just true for deep nets. I think for neural networks, for our other learning machines, there's even the way that as a human designer, this is sort of something I've been thinking a lot about lately. As a human designer, we take a series of inputs. Like I'm an industrial engineer, let's say, and I'm going to build a learning machine to control a process, a chemical process, maybe that pumps like fluids from one tank to another tank, which is actually a well-defined problem. You might, as a designer, as an engineer, as someone who's trying to design the system, you might actually find mathematical ways of relating the various signals you have available to you and then stuffing them into the learning machine. You could argue that, in fact, that is the representation. That's an act of representation, the human structuring of signals and wiring them together in a way such that they can be provided to a learning machine and it can learn weights or values associated with them. So this is interesting because I like that we've had this particular discussion, because it does bring out that, I mean, you could try to represent or to interpret, but you could also form something that represents. A representation is something you can hold up and stare at. So those are two ways that I think is used, and I want to make sure that we actually got to both. So this is great. Other questions about representation, or what or why a machine might learn a representation?
I'm kind of curious because just on this topic of representation and interpretation, whether, you know, when humans are forming something to represent, whether that will affect what is represented at the end. Because I think, like, for example, if you have people who are from different countries making these models, would that affect the end result? And even if they're building it for the same purpose, perhaps the form that comes out and the shape that you look at the end is different. I don't know if that makes sense, but yeah, that's just
it makes a huge amount of sense. And I mean, this is a very, very, very important topic. We could have an entire whole long discussion, and probably should in this course, actually. Kim, this might be something that we bring in someone who's an expert in the areas of bias in machine intelligence, and we actually bring them in to talk in this course. I am not an expert in bias and inductive biases in machine learning systems, or especially deployed machine learning systems. But this is a very hot topic, and it's actually something that is worth a much more forthright and long discussion. But yes, the answer, I mean, the short answer from, again, my unexpert opinion in this particular area is that we do see a lot of bias, inductive biases, based on what the designers do. And this isn't just at the representation level, it's the entire way that we structure our algorithms. And you can see the outfall of this in everything from how images are classified on Twitter to what language models generate when you ask them questions. There's a lot of bias. And this is part of why it's so important that we have very diverse teams of people that are actually building our learning machinery of the future, so that we can help to make sure that we represent a large number of different biases. Anyway, I'm not an expert in this topic. Like, I'm not a scholar that studies bias in learning machines, but the representation is one place where, in fact, you would see quite a bit of that bias coming to roost and staying there if you're not careful in how you design a system. There's some biases that are, in fact, like if you're trying to build a prosthetic, like I do prosthetic limbs. If you're trying to build a prosthetic limb that learns about a person, you'd almost argue that, well, you want to ignore designer bias for the most part, and you want to bias itself towards the person using it. This is a system tool for a person. It should know about them and their life and their needs, and the representation should reflect things that are going to help the daily life of the person who is attached to this piece of technology. And that's again, it is a set of biases, but it's maybe less on the designer side and more on the user side. But this is, again, there's lots of different interleaved variables. Okay, I was saying, let's move from representation. We're actually making pretty good time, so I want to Kim, we're going to 3:20, right? Is that
Yes. That's
okay?
correct.
Perfect.
Yeah.
Okay, awesome. So I'd like to shift gears from representation to prediction, if that's okay with everyone. And yes, everyone's okay. Taryn, is that good? I'm going to assume yes, unless you say no, please stop by text message on the top corner. Okay, cool. Okay. So I like to start with representation, and that a machine might learn a representation because it is, in fact, a foundation for the other things that a machine might learn. And the other important category of things that I think a machine does and should learn is the category of predictions, forecasts about the future. A more general way of thinking this is, in fact, a synthesis of the patterns in the world that it exists within and how those patterns might unfold in the future. So representation, prediction, and control. Prediction builds upon representation. You have to assume that the system is able to structure its world in some way, but then once its world is structured in a certain way, once it's able to structure the sensory motor information flowing between it and the world, then one would hope that it can begin to learn the immediate or the temporally extended patterns in the world around it. So as sort of a view into the forecasting of a world, that a system might begin to build forecasts about the consequences of how it's acting, about the consequences of a current situation, how that situation might change over time. And that might be over various different timescales. What's interesting is that, like say the cat classifier that you probably have all talked about, or the something classifier you might have seen, could almost be thought of as taking the immediate input and predicting the immediate consequences of it. That it has a very, 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 very short time scale of the kinds of predictions it's making. And that if you were to say, how will the stock markets unfold over the next, say, 6 months, which is a question I think on everybody's mind right now, then you might say that that's a longer time scale prediction. And you might say, how long will the human species last? That's a really, really, really long time scale kind of forecast. But all of these forecasts on all those different scales are, in fact, presupposing that there are patterns in the world and that the system can, in fact, learn to capture some of those predictions in the world around it. So I'd like to sort of, just as sort of a A/B for this particular part of the discussion, you can think about predictions about the next step or the thing that will happen immediately next. Or you can think about predictions about a window of time over which you might sum the thing that you are interested in. Does that make sense? Just like nods or shakes the head. You can shake your head. I'd be okay, and I'll unpack more. Okay, cool. The example that's usually used, and that I see that I know Rich has some really awesome old time slides with, where you actually had like transparencies and you wrote on the transparencies. Maybe some of you remember this. I remember having lectures with transparencies. Math was the worst because it was like the transparency being erased as it was being written. But the transparency that Rich uses actually is like rainfall. So if you're a learning machine, you might wish to learn based on the current situation or the current day, how much rain is going to fall tomorrow. So if I asked this question this morning, I would have been answered, well, I'll be walking my dog in the rain this afternoon, which I did. About lunchtime, I went out for a walk in the rain with my dog. But you might also ask a question, how much rain is going to fall over the next week? Now, there's something different about that. Is now it's asking a question, it's making a prediction. It's a learned forecast. You're trying to learn to predict a quantity that is not a momentary quantity, but a quantity that is actually summed over a window of time. And importantly, you might actually want to sum over that window of time where different parts of that time scale are weighted differently. Great example is like, hey, is it going to rain over the next week? Well, if I'm going to be stuck in my basement like I have been since March, it maybe doesn't matter too much if I'm going to be, like during weekdays, maybe it doesn't really matter if it's raining outside, but I might care a lot about whether it's going to rain on the weekend where I actually want to go bike riding with my wife or take my son and our dog out for a walk in the park. So you might imagine that the way that you sum over the future in terms of the predictions that you're making as a learning machine might actually be different. It might be weighted over the future. You might care what's going to happen next spring a lot in terms of like what's summer going to look like next summer, but have little interest in forecasting what's happening over the winter, even though you're still summing that whole window of time. Does that make sense? Like that there's momentary and then there's temporally extended predictions, and that there might be weightings over those predictions in time. So with that in mind, questions about learning predictions. Why a machine might learn predictions, what kinds of predictions a machine might learn, why it should even do that. Is the representation already learning predictions? So why do we separate them? All these kind of questions, if you have them, now is a great time to open that particular debate.
But it would take a lot of data to predict appropriately, right? They would, let's say for the weather, because it sucks. Personally, it's like in Edmonton, every time that you ask, it's like, oh, is this going to rain? And it's like, oh, 10%. And you're like, I'm not taking an umbrella. And actually, that day, it drenches you to the bone. And now I think, oh, probably what it means is that in 10% of the day, there will be rain. But no, so do we have enough capacity for these machines to store the information of each day of the past 50 years so that it can make an accurate prediction? Or have we not reached that point in which machines can store that previous information to make a proper prediction in the future?
Cool. Oh, you're getting into like things that we probably won't. I had on the register for talking about later, but we probably won't have time for. So it's great we're getting to them now. There's a really interesting thing. Like imagine a world where we do have weather data, and let's just imagine a magical fairyland where we've managed to store all of the weather data since the dawn of our species. Like someone was like etching stuff on tablets, or like, I don't know, making patterns of cows in a field and then painting them on stone to actually show what the weather patterns were for thousands and thousands of years. Let's imagine that was the case. Okay, cool. So if that was the case, you would assume that we can somehow, again, with a magical learning machine, capture all of the patterns within that data to 100% fidelity. Like we can actually represent, I'm going to say represent again, we can represent all of the patterns that are captured there. And if any of those, if we were to go back to any point in that history, that we would be able to know what was going to happen with perfect accuracy. Let's imagine, this is a really extreme example. We have a learning machine that we did store all the data, and it can actually represent, it has enough capacity. The machine itself isn't just storing all the examples, but that its internal structure is sufficiently complex to be able to hold the relationships between all of the different elements of all of those samples of data over all of the past. So it in some way can form a representation in the sense of the thing we hold up and look at of all of those patterns. So representational capacity and data storage is both there. Now imagine something happens that's never happened in the history of the Earth. And I'm trying to think of something really good, but maybe a really good one that we certainly wouldn't have data for is like, I don't know, the sun goes red giant or something like that. Like right away, it's like, oops, just tomorrow you flip the switch, the sun grows to size, it like absorbs Mercury and maybe Venus, and the planet gets really, really hot. I mean, in a non-stationary environment, this is my way of like using very extreme examples of branching into a case for non-stationarity. So even if you did all of those things, you would be in either in one of two situations. One is that you're in a state that the system has observed in some way, shape, or form in its past data, but there's absolutely no way that if you actually were to like roll forward 100 years into the future, and then compare the predictions to what really happened, there's no way that those things would line up, right? Like it's now where everything on Earth is probably being scorched by the flares of the red giant. This is like going to be a horrible situation, sort of like the end of the world from the Time Machine. But in that respect, you could say that even if you did have a good estimate for the present, even if you could make an estimate for the present, that if you were then to look at the accuracy of that estimate or the way that that estimate actually forecasted the events of the future, that there's no way that those things would line up. The other thing you might imagine is that, in fact, like all of the Earth is on fire. This is really bad. Wow, we don't actually have a recorded data point that looks like that. So there's no data that we could appeal to. There's nothing in the wealth of information that we have stored that allows us to, with any hope, even say what's going to happen right now, let alone over some window into the future. So this is the non-stationary world, and the case that learning machines actually need to continue to update. And their estimates, I mean, there's no crystal ball. We get crystal balls because we rely on regularities in the world, but there are certain discontinuities that will confound even a machine that had lots of data. So let's imagine that our world is mostly, slowly changing. So we can assume that a system that stored all of the history was able to, in fact, make reasonable predictions, and there might be a little wiggle in terms of how well they panned out in the end. Then you could say, well, now the second piece is, well, you just said exactly that we can't store all of the past information since the dawn of our species and before. That is probably not something we can do. We don't have the computronium for it, even if we wanted to. So machines are now trying to remember the past in compact form. The extreme of that compact form is essentially the Markov assumption. Maybe Rich went through this in the materials you saw from him or any of your readings, or maybe Osmar did as well. But the assumption that the present state of the world sums up everything that's happened in the past. That's a pretty extreme assumption. But you might imagine that that a system would require some form of history or some form of assumptions about how the present signals relate to all the signals that have happened in the past. And the degree to which you try to compress, compact, smush, or abstract away that infinite history, because it is infinite. Even if I were to say between now and now, there's an infinite, unless time is truly quantized, there's an infinite amount of space between those two moments. So we have to in some way start to be compressing the time involved, the samples involved. How you do that will even in a perfectly stationary world determine how well the system is able to predict something into the future. But in essence, it is especially statistical machine learning. You're taking those samples from the past, you're updating the structure of the learning machine with them in one way or another. It may include a history, it may not. It may just include tuning the little mathematical knobs of the system, the weights in the system that are giving it its power. And that will determine the future rollouts. Let's move. Sorry, that was a really long soapbox part on my part. Hopefully it was worth the time that we spent on it. But any other questions or thoughts about prediction or how a machine might learn, what a machine might learn in terms of prediction? Okay, if there isn't, I'm actually going to jump right into control. Not because I don't want to dwell on prediction. I've actually dwelled in my academic career. I was doing a lot of control learning research, and then about a decade ago, I just started working on prediction, and I haven't really stopped. So we could spend certainly more time talking about prediction, but I think right now is a great time to think about not the representation or the structure of the information in the world or the forecasts that are built on it, but in fact then the decision-making capacities of a machine. And so this came up at the very, very beginning when we were defining intelligence. The learning of decisions, or the way learning how to make choices with respect to the stimulus that you see or to the models that you have about your world or the plans that you might have formulated. So how does a machine make decisions? There are many different ways that we might imagine, but right now, to begin with, maybe some reactions or some questions regarding what a machine might learn with respect to its decision-making in the world. And maybe, Eduardo, you've given many good comments. Let's let's see if anyone else has any comments, just to make sure everyone's getting some equal voice in the discussion today.
I have a comment in terms of the predictions. So this is something, I mean, it's happening these days. I have experienced some. For example, if I am, looking to purchase an item or something on Amazon or, just in Google search, I would see more ads of that items coming in other apps. So this is something I believe that's a prediction that for example, the smartphones learn that if you are looking for something that would give you more choices of that thing that you have looked for, even if that didn't happen in the same app. So this is what came to my mind when you said prediction.
And this is really cool because it also addresses our current, like the example you just gave is a great one because it ties together representation, prediction, and control. So you might imagine that the system is able to represent in some way your browsing habits, maybe your purchasing habits, depending on what it sees in the world. And I'm never quite sure what different systems on the internet see. But imagine that it has some way of representing your patterns and habits, and maybe the patterns and habits of others as well. So based on that and the current, based on its ability to represent patterns of users and what you're currently doing or what you have been doing, you can imagine then making a forecast about the thing you might like most. Or maybe it makes a forecast about a set of preferences that you might have. These are predictions about the kinds of things that you might buy. Now it's faced with a decision. Like there's like in the case of online ad serving, and again, I know very little about online ad serving. My colleagues, people like Chaba, know a lot better how bandit systems work for serving ads. Bandits are not like people that try to take your money. Well, maybe they are actually. Bandits are not like people that take your money, but they're like a problem formulation for machine learning where you have multiple choices and those choices have outcomes or payoff mechanics, much like slot machines in a casino, but they don't rely on the state of the system. Anyway, that's the kind of bandits I mean, just to be clear in my terminology, not people that take your money. But that even in case like that, the system will be forced to take a selection of possible ads it might show you. That's probably a finite set, or it's a continuous set, but it comes from some distribution. And so now, how does it show you one of the many potentially infinite numbers of ads it might have? Let's imagine there are a fixed number of ads. There's like 300 people who've signed up for ad services with whatever web company it is that you're doing your search through. Then it might have to choose which of those people, which of those companies to pull the ad from, and then which of the ads that company might have. It might do that based on learned prediction. So you're like bang on there. That is actually how it might look at the prediction that you might buy any of these classes of products, and then take the top 5 and roll like a five-sided die over that. Or it might just take the absolute most likely thing that it predicts that you would be hoping to purchase. And this is a great example of prediction feeding into control. In control, you might think of this as forming state valuations or action valuations. This is a very normal way for machines to make decisions, but it's that essentially they say, oh, of all the possible states that I could be in, all the possible situations, what is the predicted value of each of those situations? The goodness or badness with respect to whatever criteria the system has for assigning goodness and badness, and then take some action either in a very deterministic way or in some kind of probabilistic way to select from those many alternatives. It might also actually start to assign value to actions in situations. Like, oh, if I were to, given that I'm like on this web page and I could serve these 5 ads, which of those 5 ads as an action, these are decisions it could make, which of those decisions would be the most valuable, and then pick that decision. So those are very strong ways that you might imagine the output of prediction being in fact the roster of choices that are held up for a machine to make decisions based upon, and it can select one of those based on the relative valuations that it assigns to its predictions. So that's a great example that you brought up, because it is hitting to the very heart of how you might choose actions or make decisions based on predicted values or expected future outcomes. Does anyone else have any thoughts on the way or the whys of how a machine might make decisions or control decisions in its environment as it interacts with that environment?
Kind of just going off what you said as well, and some of the conversation that we had earlier, just focused on maximizing value. So however that's assigned and whatever criteria is determined when designing these systems, whether that's to maximize your profit or otherwise, I think that would be how they would make those decisions, and then just kind of assigning different weights to the inputs to be able to maximize that final output, I would say.
Cool. And what's also really cool about your comment is that it speaks to another way that we might, like we just talked a lot about how you might hold up and choose between a number of different valuations or the values over different actions that you might take. There's also settings where you might have an almost infinite number of actions that you might take, or your situation might be very, very smoothly varying. It's very hard to identify discrete states that you might be in. So if you do have a good solid notion of your long-term valuation or the returns that you might be getting along the way, like, yeah, I served this ad and that person actually bought it. Cool. And then that company that served the ad has to pay the ad serving company some amount. And then but that company also gets, anyway, there's some way you might say this was good or this was bad. One thing you could do with that notion of the goodness or badness, either immediate or very temporally extended, is to build up the values we just talked about. Another thing you might do is to say, well, was that really good? Cool. I'm just going to bias what we call a policy in favor of the action that we just took. Now, this is subtly different. It's really important, though, is that you might think about what we call a policy as being the mapping of a situation, the state of the world, into the action or actions you might take in that state. One way to think about building up a policy is the valuations we just talked about. Another is to take the ongoing stream of signals of goodness or badness and use those to nudge or tweak or sort of push the policy one way or another, so that the system will, upon entering a given situation or a given state or a given set of observations, will be more inclined to take one action over another action. So this is really saying that long-term outcome or short-term references towards that long-term outcome are being used to nudge the policy, nudge the mapping from states to actions one way or another, so the agent's more likely or more biased to take one choice or another choice in a given situation that it's seen before, or situations like that one. So this is great because we just covered the two big topics I was hoping to cover with respect to control learning, which is learning based on valuations, learning how to decide based on valuations of the world around you, or learning based on the modification or altering of a policy that you have, which maps the situation to the actions that you might take. Those are both really good examples of it in those last two comments. So we are now at 3:15. So I want to do a quick summary, if that's okay, for just to say what we've talked about and to sort of cast a little bit of light on some of the other implementation details. So we talked about intelligence. We talked about intelligence in terms of representation, the way that the system might begin to learn how to structure the information in its world, about prediction, how a system might begin to build forecasts or expectations over the way that representation might evolve over time. Maybe that's when we say it. And then control, the way that it might make decisions, not control per se over its world, but control over its own interactions with the world. How it might change the way that it makes decisions based on that representation, and the expectations of how the information that representation conveys might change over time. You might ask how that learning actually, like boots on the ground, brass tacks, how this actually unfolds. There's three big classes that we don't probably have time to talk about today, but I just want to mention, and because I'm sure that you've already talked about them. One is what often is called supervised learning. I see some nods. You've heard about supervised learning. Essentially, the process of learning through labeled examples. This is what I wanted you to get. This is what you said. Make that more like this. So that's the process of learning through labeled examples. So you might learn those things I just told you about, and we just discussed at length through learning via labeled examples. You might learn it in a unsupervised way. So people have probably also heard about unsupervised learning. It's kind of still supervised. Let's be reasonable. I mean, there's some kind of measure that's being used for the system to change the way it's structured. But for the large part, you could think about unsupervised learning as learning through the inherent structure of the data based on some measures over that structure. So you might say, like, I want to learn a representation based on making different inputs as different as possible from each other in terms of how similar inputs might be assigned. So learning through labeled examples, learning through the structure of the data, and the one that I actually study, which is learning through trial and error, learning through experience with the world. And you've probably heard that called reinforcement learning, but you can think of it more generally and in a much more plain language way as you can learn the prediction and you can learn representation and control behaviors through trial and error interactions with the world. And just to sort of wrap up and then may go into question time, when that learning occurs is also really important. So you might imagine that the learning of representation, prediction, and control happens before a system is ever really deployed in the wild, squishy world around it. You might do something like taking a bunch of samples, or like Eduardo mentioned, we have some big history. I extend that to the history of our species, but you might take all of the examples you've seen before, put them into a giant vat with a stirring thing and cook them up and boil them down, and then hand them to a learning machine as its weights or as its internal structure. We'd call that offline learning. Essentially, that the system is learning from data that is not in its current flow of experience. You might do something that is similar to that, which is called batch learning, which is you store up a bunch of examples and then you boil them down and then you hand them to the learning machine, and then it interacts with the world and builds up more examples. And then the final case is incremental, or what we might call online learning. Word of warning, if you publish a paper that says online learning, you get invited to a bunch of conferences on online education. So online learning is not always the same thing to every possible community. Just as FYI, I'm still invited to online learning conferences, but not the kind that I would normally be an expert at presenting at. So the online or the incremental learning setting is, in fact, that after every possible interaction with the world around it, the machine updates its internal structure, changes its representation or its predictions or its control decisions. And so that's the sort of the continuum. And there's many granularities, there's many ways you might see this manifest, but the learning of prediction, control, and representation might be done through a different set of optimizations, the structure of the world around it, trial and error, or through labeled examples. And that might happen in large batches, in extremely large batches, or through the immediate interactions the system has with the world around it. And so putting all of that together, like, I didn't give you much that was technical today. I didn't tell you many specific examples or case studies, like I'm sure Osmar, if I know Osmar's usual lectures, I'm sure he gave you plenty of excellent case studies. But today, what I was really hoping is that through our discussions, that we're able to unpack a little bit what's going on under the hood in all of the other examples that you have seen, or that you might actually see. And I'm not trying to say that you should use the breakdown I gave you today as the correct breakdown. The idea that intelligence is the computational part of the attainment of goals, or that really you should always view a learning system in light of representation, prediction, control, and perhaps some of the meta control or the meta learning that happens on top of that. Or that you should view it in terms of the three breakdowns of supervised and unsupervised reinforcement learning, or that the batch or the incremental or the offline distinction is the one you should always use. But these are, much like Rich's mystify and demystify, these are thinking tools you can use when you're unsure about how to reflect upon a machine learning or an AI problem. These are thinking tools you can use to help you work your way through what's actually doing, what is it actually learning, and what aspects of intelligence is this system actually engaging with to do whatever role it has in the world that you are seeing it interact. So with that, we have no minutes for questions. But I think that's okay because we had a lot of questions all throughout. So thank you all for being so engaged in the discussion and for making this a really lively chat. Kim, I hope this was what you wanted to get. I change my lectures every single time I do this course. So Kim, like, learning through trial and error, was this okay? Or should I never do this ever again? Okay, cool.
Well done. Yes. Yeah. Cool. Okay. Well, thank you very much for that. And on Tuesday, we have quantum supremacy. And then on Thursday and then next Tuesday, we have quantum biology. Yeah. So anyway, that's what's in your life. Yeah. And then Nishita Mogi is going to teach you. And then there are a few invitations out for people to talk after that. So there's a little bit of flex still in the end of the schedule.
I was on the ball this year, Kim. I got back to you on time.
Yes, I know.
For once.
That was totally cool. Okay, thank you again. Have a wonderful Thanksgiving, everyone, and we'll see you next week. Okay.
Bye, everyone. Thanks so much for the wonderful
Thank
session.
you.